Hey everybody, how's it going? This is me, and today we will talk about how can we focus gas production rates and using the graphical analysis, we can actually look at how are we able to predict the production rate, maximum flow rate, minimum flow rate, and also using pressure against cumulative production plot to actually estimate the gas initially in place. So today video is solely we're gonna focus on these principles, and the image you're seeing at the moment is me. I'm the main talker today, where I'll be sharing you and working through actual exercises together with you. If you feel interested, you could just create an Excel sheet and work along with me. I'll be also explaining you about the principles behind these calculations, and also explain to you a little bit deeper into how can we use the graphical approach to actually estimate these things, which are very important for the oil and gas production and the production forecastings and investment returns, etc., etc. So I actually thought to divide today's section into two parts. One is to talk about the to talk about the gas production, and later we will focus on the oil production. So gas production is much more easier to calculate using these graphical approaches, but the oil production is slightly more complicated because we need to use material balance approaches and things like that. So today I thought maybe we could just go over the gas production and using a simple analogy and constraints to actually predict and forecast gas production rate. And if we have time, we can go over the oil production prediction as well. But I believe because we have limited time allowed for the video recording, we will just go with the gas production first. Okay, so let's get this out of the way. So just to show you, this is me, and I'll be talking you through this exercise today. Okay, so what was I talking about in terms of gas production using the graphical analysis? So this graphical analysis is known as the inflow performance curve against the vertical flow performance. So today the section, I believe, if you don't really understand the reservoir principles and don't know the basic terms, this video may not be the right one for you, because I'm going to talk you through this exercise assuming that people who are watching kind of understand the basic principles behind the reservoir production. Nothing complicated, just basic terms. Okay, so when we actually try to predict the gas production, what do we need to know first? We need to know the basic principles, such as there must be a pressure drawdown, which is the difference between the reservoir pressure minus flowing bottom hole pressure to create the pressure difference, so that the well can start to flow. And using this very simple concept, we can actually focus how much amount of gas are we going to be producing, such as what is the maximum flow rate per day, what is the minimum flow rate per day. So in order to do that, we first need to look at this graph here. So which is, let me move this window out of the way. So let's zoom it a little bit more into here. So here, this graph is what I was talking about, calculation of rate into the well bowl. So there is a bottom hole flowing pressure, as you know. As we started to produce from the reservoir, it is inevitable that the reservoir pressure will start to come down, after some times of production. It really depends on us to actually, re-inject, so that we still have the reservoir pressure not completely diminishing. Okay, so bottom hole flowing pressure, as we produce days, months, and years, reservoir pressure start to decrease, and that also applies to the bottom hole flowing pressure. So bottom hole flowing pressure will also start to decrease with time, and with that we will have a rate production profile. And then there we have a two scenario. So as we can see, the drawdown is 5,000 psi using this pressure as a reference point. So at this point, what is the bottom hole flowing pressure? You just need to, draw a straight line across this intersection line. If I just show it right over here, if you just draw a correlation line, this is a terrible line. However, and you can actually estimate what is the bottom hole flowing pressure at this intersection point. Okay, that is basically how you predict the bottom hole flowing pressure and also predicting the drawdown. So you can see that there is a two graph, right? One is a straight line, another one is slightly curved. So there is actually different ways of how these bottom hole flowing pressures decreases with time. And one is a very simple one, which is flow rate is equal to productivity index times reservoir pressure minus well flowing pressure, which is actually the bottom hole flowing pressure. And another one is slightly complicated. If you have a lot of data, such as the permeability, you have the viscosity, formation volume factor, and also wellbore radius, and reservoir radius, etc., and the skin as well, then you can more correctly and accurately predict how the bottom hole flowing pressure decrease with time of our production. And these could either give you a linear straight line or a slightly curved or exponential, kind of curve. And using these two profile, and in combination with what I was talking at the start of this section, which is the vertical lift performance curve, which looks like this, and we can actually start to predict. So okay, look, so you see this curve, right? And if we use this curve over this graph, let's just say over here, like this, and then we can start to estimate the production points, and what is the minimum amount of productions that we're gonna get, and also how can we enhance the production using these curve, and what kind of constraints that we can apply so that we actually can widen the curve. If you actually widen the curve, the rate's gonna be different, which we will talk about that later on. Okay, this is the idea behind how we can calculate it. So for today sections, I don't have these permeability data and viscosity and also formation volume factor, etc., etc. So we're just gonna walk through a simple linear relationship between the flow rate and the bottom hole flowing pressure, and using these vertical lift performance curve, we will actually start to predict what is the maximum flow rate and what is the minimum flow rate. Okay, so I think this is enough about getting you a bit of a summary information over what we're going to do with this graph. Now let's actually focus on the vertical lift performance curve. So what does it actually mean? Lifting basically mean we're trying to once you actually perforate into the reservoir interval, there needs to be some sort of force to make sure that the well flows into the reservoir, right? Into the surface facilities, and you can actually distribute it to the markets, etc., etc. So vertical lift performance curve is VLP for the abbreviation, and this actually comes from the well sizing, which we will dive deeper in the later of this video. However, this is important where we actually talk about the concept of how do we actually predict these maximum and the minimum flow rate. So this is very intuitive. As you can see, these labels are pretty much self-explanatory. So we have the reservoir pressure over here. As the well started to flow, the pressure decreased. So as the well started to flow, we have pressure decreasing, and just like that, the bottom hole flowing pressure profile will start to decrease. In this example, this is kind of like a little bit of a curve, as we can see above there. The example, slightly like this, because we have a lot of data in here. But if we have a straight line, this is possible too. What I'm trying to say is there could be different scenario. It could be just a straight line as well. Okay, so okay, I must remove the circles. Okay. Yeah. So what's going to happen is we have the vertical lift performance curve, which is green curve over here, and we have also bottom hole flowing pressure decreasing profile. This is called IRP, which is inflow performance curve. You see, inflow performance curve, and the point where these two curves intersect is the point where we will have the maximum flow rate. Oh, sorry. And the point where the bottom of this, vertical lift performance curve or green curve is where we will have the minimum flow rate, or otherwise known as a stall point. So stall in its own meaning is actually stopping of production. So basically meaning that we have a production range in this blue arrow showing the minimum and the maximum production rate, and then we can actually get the idea, okay, what kind of flow rate are we gonna get, and also what kind of flow rate are we gonna get, and what kind of facility that we need, because you actually need to consider regarding to the flow rate, you need to actually consider about the capacity of your facility, right? And then only in that way you could do some sort of chemical processing, blah 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 blah. You guys know that, right? Okay, so this is how we actually predict the maximum and the minimum production rate. And as we can see here, this actually depends on the vertical VLP, which is vertical lift performance curve, the green curve, as I said, which is from the well sizing, and also IPR, inflow performance curve, which actually depend on the numerous factors, which is permeability, viscosity, formation volume factor, etc., etc. And then we could have different production profile. And later in this video, after we run through all these exercises, I will be showing you how can we actually predict and how should I say modify different approaches to boost the reservoir production, or sort of kind of like extend the production life, even though the the production has been for quite some time. You want to scrape the barrel, right? You want to get out as much as you can get out from the reservoir. So we can do that in the later part of the section. Okay, so the most important information that I just share you right now is first of all, bottom hole flowing pressure rate, and we have the inflow performance curve, which is the same as over here. We can have two different scenarios, and then we have the vertical flow performance, and starting from there, we could actually predict maximum flow rate, minimum flow rate, etc., etc. Okay, so now this lead nicely to the place where we have to predict the gas initially in place, or hydrocarbon initially in place. And okay, you might ask, okay, why do we need to do that? So you need to do that because knowing that will actually help you decide about your business operations. That's the first thing, whether the project is profitable or not. And the second thing is you can actually use this, gas initially in place value to actually calculate the recovery factor, these kind of numbers, which are very useful for the operation, to make sure that you are actually producing in a reasonable and decent profile, not like sort of walking blindly when you're producing. So you need to know the initial starting reserve that is already in place, and you need to actually walk through after you have produced, and how much amount of gas is left to produce, etc., etc. Okay, so this graph you see is P over Z against cumulative production profile, and this is only applicable to the gas when we actually estimate the gas production profile. We cannot use that for the oil production profile. Okay, that is not oil production, sorry, oil initially in place profile. We cannot use that if we want to use oil initially in place techniques. We need to use the material balance approach, and maybe proper geology approach, such as drawing the area depth profile and actually calculating the amount that is within the curve, blah blah blah. Okay, so basically the most important thing I was trying to say, this is only applicable to the gas itself. Okay, this is what I was trying to say. This is only applicable for the gas. Okay, so P over Z, which is basically mean pressure divided by Z as a compressibility factor. And we got the profile over here. And then we have the cumulative production profile, which you gather as you produce. And what we're going to do is, let's stop imagining this a compressibility factor for a bit. Okay, let's consider that it doesn't exist. As we actually start to produce, as from the reservoir engineering point of view, the reservoir pressure will decline, right? The reservoir pressure will decline, and this declining reservoir pressure value divided by the Z factor, which is a compressibility factor, will give us the some sort of profile, which is plotted against the cumulative production profile. Okay, so just like that, what are we gonna have is we're gonna have a relation, which is a pressure drop against the cumulative production profile. But it is important to remember that this is not a simple pressure drop. It is pressure drop divided by the gas compressibility factor. Okay, and we can actually extrapolate this, declining trend to actually straight line linear extrapolation, and then the point where it intersects the cumulative production profile is our estimate of a gas initially in place. Okay, and we can't actually let our reservoir pressure to go down to up to the value of 0, right? There must be the abandonment pressure where you must actually leave things in behind, unless you risk breakdown of the reservoir formation and operational failure. And so what we need to do is we actually need to abandon at this pressure. So this entire area is gonna be the actually how much amount you have produced. And then let's say we have produced a G amount of gas, so we got G amount of gas produced divided by gas initially in place, which is where this line intersect. What we're gonna have is we're gonna have a recovery factor, okay, which is very important for the oil and gas operations and hydrocarbon recovery operations. So by knowing that, what we can actually do is we can actually use this graph in our exercise, and then what we're gonna do is we're gonna actually calculate how much amount we have actually produced, how much amount we have recovered, and how much is left there to be recovered, etc., etc. Okay, so the important thing to remember is I said to you that we have some sort of a linear profile, right? This is like a very good fit line, a straight line. The idea is, yes, we need to like extrapolate linearly straight line, but this pressure trend does not always follow to be, placed in place with the straight line extrapolation. So we can have some sort of profile like this over here. Okay, so we can have, oops, let me actually, what we can have is a profile which looks like this over here. So as we just look at it, we have a P over Z profile, which is like pressure divided by the compressibility factor, right? And then we have the pressure decline, yes, and then the pressure trend start to deviate from the initial production trend. Oh, sorry, declining trend. This is because of the aquifer support that can actually, alter the, declining profile, declining trend. And then if you try to extrapolate, starting from the point where the, pressure profile start to deviate from the original profile, you will get the false estimate of gas initially in place, and this is a very bad thing. We don't want the false estimation of our estimation of the gas initially in place, right? Because this really depends on your business returns, investment success, and how much you need to actually spend from your pocket actually before you actually yield something. So this is important that we need to know if we are encountering a gas reservoir which has a aquifer support, the pressure declining trend could actually deviate from when it start to decline. So we always must stick to this trend where which is the start of the reservoir pressure and its initial declination trend. Only in that way we will be able to predict a reasonable estimate of gas initially in place. Even then, this is not very accurate, right? So we can actually use the material balance approach and other factors such as maybe subsurface computational software like Petrel to actually estimate how much amount of gas initially in place, and we can compare, contrast, and actually come out with the uncertainty range of our gas initially in place estimation. Okay, so I think this is enough for actually introducing what will we be doing. So we'll be using this P over Z profile against the cumulative production profile to estimate our gas initially in place, and then we will use this inflow performance curve and the vertical lift performance curve to actually estimate the as I said, maximum and minimum production profile, and how are we gonna actually estimate the recovery factor, etc. Okay, so I have the spreadsheet ready, which is over here, and then let me move this to here, and we will actually look at with the real data, but it's gonna be very simple exercise because if we add a lot of complicating factors, it might take a lot of time, and the video has a time limit as well. So let's just go through a simple gas field exercise where we can actually get the idea of how these things are done, and we can actually calculate to get the amounts that we are looking for, and hopefully this can give you some sort of idea over how these performance are predicted and rates are forecasted. Okay, so we got a question over here, which is a gas field has an initial pressure of 3,700 psi. Okay, this is very important. Initial pressure basically meaning that this is the reservoir pressure, right? And then based on analogs, assuming volumetric expansion only, that is no aquifer. Okay, this is very important as well, no aquifer. So as we just talked before, okay, the aquifer can actually, cause the deviation of the pressure declining trend, and therefore we don't need to worry about that here. Estimate, so it wants us to estimate, gas initially in place in MMM SCF, okay? So when we calculate these reserve and resources and recovery factor, it is important that we understand the units and the amount. Depending on that, even a just 1 0 after the value can be a very, very big difference. So I wrote down a simple representation of the unit. So mm is actually million. Okay, this is very easy to understand. Mm is million, and million is actually 10 to the power 6 in the oil and gas industry, and mmm is billion, okay, which is 10 to the power 9. Okay, so that means 1 m is equal to 10 to the power 3. Okay, mmm is 10 to the power 9, which is billion. Million, which is 10 to the power 3, 10 to the power 3, making it 10 to the power 6. Okay, so if you feel a little bit unclear later in this exercise, which even I have this kind of confusion, just come back to this part of the video where I explain about how we actually measure the amount in millions and billions and stuff. Okay. Okay, so the question asks us to actually, estimate gas initially in place, and they gave us this profile over here. This is actually given. So it has no aquifer, as they said. So what do we need to do over here? Okay, in here, we have a pressure declining trend. Okay, and as I said, we always have to start from the reservoir pressure, and the reservoir pressure is given as P reservoir is 3,700,
And just because we don't have any aquifer means that we don't have any deviation from the main pressure trend, right? So we can actually start from 3,700 psi, which is a reservoir pressure, and just extrapolate that line till the end where you could actually intersect the cumulative gas production profile. But what we need to notice is this is not pressure itself, okay? This y-axis is not the pressure itself. It is pressure divided by compressibility factor. Because we are not giving any compressibility factor, we do not actually need to do that, which is, reservoir divided by the compressibility factor, and we will be getting a different value. So in this example, we will just do it from the reservoir pressure because we are not given any, compressibility factor. And that's why I started my line from 3,700. And just looking at the trend, I extrapolated this line linearly, straight line, till it intersects the cumulative gas production. And if we go back and look at our, technique, once you intersect at the bottom of the exit for cumulative production, you get the estimate of gas initially in place. Okay, so now that I have intersected that, this point over here, let me change the color. This point over here, we have the gas intersection point. Now this is our gas initially in place estimate. Okay, so now let's go and have a look at it. How much is it? Okay, so we're given 200, 400, 600, and 800. Okay, so that means 100, 200, 300, 400, 500, 600, and this must be 700 MMM SCF. Okay, SCF is standard cubic feet. Okay, so I have actually written how much is it here. Very easy. We just linearly extrapolated from a graph, and we have actually got the gas initially in place, which is 700 MMM SCF. Okay, and just because I explained to you MMM is actually billion, I have written down gas initially in place, billion standard cubic feet. It should be BSCF. It was my mistake. Billion standard cubic feet, and then we got 700 MMM SCF, which is BCF, which is MMM, as I said, is also a billion. So I just written down as a billion by reading from this graph. So we got the gas initially in place. So how are we gonna actually estimate the rates and stuff? So let's go a little bit further down into the questions and let's see. Okay, so we got, given that the productivity index has been estimated to be 10 million, 10 to the power 3, 10 to the power 3, making it 10 to the power 6 million standard cubic feet per day divided by 1000 psi. Use reservoir inflow performance and vertical lift performance curve to estimate maximum well flow rate, Qmax, as in per well. Okay, so what are we given over here? We are given the productivity index, which is 10 mmSCFD divided by 1000 psi. So I wrote down, let me zoom in a little bit. I wrote down productivity index, which is SCFD divided by psi as given, and 10 divided by 10,000 give us 10 to the power minus 2, right? So our productivity index is 0.01. Okay, so we got this one. So what does it say? Use reservoir inflow performance and vertical lift performance curve to estimate maximum well flow rate, Qmax. Okay, so we are given this curve over here. Okay, this is the given original curve. If I just show you, so this is the curve that it was given. These lines and stuff, I drew it later when calculating it, so just so you know. Okay, so what do we need to do first? Okay, we have the vertical lift performance curve. Okay, vertical lift performance curve. This blue line over here, this is a zooming version of this, profile. This blue line is a vertical lift performance curve. Okay, just to recap, you see this vertical lift performance curve, the green one. Okay, that's the one that we are talking about. So what do we need to do? We need to create these one of these profile, right? Only then we can actually look at the intersection point and actually look at the maximum inflow performance, etc. Okay, so as I said, we have two types of scenario. Given the data, we can actually calculate how they are declining, but in this example, we are not given any, permeability height and viscosity, formation volume factor, skin factor, etc. So we're just going to do a simple one, which is flow rate is equal to productivity index times reservoir minus well flow. Okay, so let's go ahead and do that. Why don't we do that? Okay, so let me just actually copy it and paste it over here so that you know what I'm doing. So you see, I just told you that this is the one that we'll be using. So we are actually have to calculate the flow rate against flowing bottom hole pressure. Okay, so we got the reservoir pressure, which is from 3,700. This is where we have to use it as our starting point. Okay, so flow rate, we got the productivity index over here, and then we got the reservoir pressure, and then we got the well flowing pressure. Okay, you might ask, okay, how do you get the well flowing pressure? Okay, bottom hole flowing pressure basically is starting from the reservoir pressure till it comes to 0. So this will be the P well flow. So we just got to do the formulation and calculate the flow rate. So as you can see here, let me give you the example. Okay, so flow rate is equal to productivity index, which is C3 in over here, productivity index times reservoir pressure minus P well flow, reservoir pressure, which is 3,700, minus P well flow, which is also 3,700, because remember, we have to incrementally reduce it, as we go down from the pressure value. So that gives us the rate of 0, which makes sense. If you don't actually let the well flow and create the reservoir profile, you will get the reservoir profile which is static at the reservoir pressure, which is 3,700. But once you actually reduce this, sorry, what I mean by that, once you actually create the drawdown, which is reservoir pressure minus a P well flow. Let me actually clarify what I mean by drawdown. This is actually called drawdown. Once you actually create the drawdown, there will be a pressure relief zone, and well will start to flow, and then we will start to get the flow rate of how much. So this is how the flow rate is estimated by using the formula, as I said. If you want to do it at your home, looking at the data, you can actually do it and you will get the idea. So substituting this pressure, P well flow in the 100 interval of 3,700, 3,600, 3,500, etc., you will get the flow rate. Okay, in this example, I wanted to show you a very simple calculation, so we just use the very easy number to do it. So 100 psi interval is good enough. So I created this flowing bottom hole pressure profile, which is from 3,700 to 0, and then we got the flow rate of the well, and depending on the drawdown. So what you need to do is the bigger the drawdown, the bigger the flow. So you might notice that as we actually reduce the flowing bottom hole pressure, and we are creating a bigger drawdown, and we are having the bigger rates. Okay, that's basically what I want to say. But in the real world, you can't actually do that because there are like multiple constraints, right? There will be geomechanic things that you need to consider, your well capabilities, and also the permeability factors and stuff like that. We're using a very, very simple equation to estimate the flow rate. That's why we're getting a very simple number with the increasing amount. Okay, so what is the next step? They asked us to create this, inflow performance profile. So I just want to, make sure that you understand it. This flowing bottom hole pressure and the rate, this relationship is actually, this relationship is actually inflow performance profile, inflow, performance profile. Okay, So we got this profile, and we are given the vertical lift performance curve, and then we can start to actually estimate our flow rate. Okay, so considering that you understand this, I will get rid of this. You can actually come to revisit this part if you don't understand it. We have a very, very tight space here, so let me just get rid of it very quickly. Okay, so what do you need to do? We actually need to create the intersection point. So we got the given vertical inflow performance curve and vertical lift performance curve, and we have created ourselves a vertical inflow performance curve, and we have created the pressure intersection points, and using that we can actually estimate the range of the flow that we'll be getting. Okay, so if we go back to over here, this is how we estimate, right? The point of intersection is the maximum flow rate, and the point of the bottom of this vertical lift performance is the minimum flow rate, which is called the stall point. So our production range will be from here to here. So the range is here, right? So the range is, let's say, maybe 7.5, let's say 7.5 million standard cubic feet per day to possibly, this is 23. Okay, so 7.5 to maybe 23 million standard cubic feet per day is our production range. Okay, with this being the maximum, the intersection point, and with this being the minimum, which is the minimum flow rate. Okay, so to make sure you see this, so this is maximum flow rate, and we got this as the minimum flow rate. All right, so let me just get rid of this because we're going to be using this graph a lot. Let's not actually throw a lot of things on it. Okay, so now you get the idea of how these flow rates are estimated. Let's see what is actually asking to do in terms of questions. Let's go back here. It says calculate. They asked us to estimate the maximum well flow rate. I think we just did. We just looked at the graph and estimated the maximum well flow rate. So I have actually written down the maximum well flow rate, which is 23. Okay. I've actually written down as a 23 because I consider this intersection point is more or less equal to 23, maybe slightly different with the decimal places and stuff, but I just didn't want to complicate this thing, so let's just keep it as a 23. For some reason I couldn't. Okay, let's stop sharing for the moment, and then let's start the sharing because we need to show the formula of how these actually are calculated. So I need to look at this. Right, we're back. Kind of have a issue with my Excel sheet, so I had to actually restart my Excel. So now what we are talking was we actually estimated the production profile from the maximum flow rate and the minimum flow rate, and we got the range already. And the question actually asked me to estimate the maximum well flow rate, which I have estimated at this point over here. Okay, let me actually. This point over here, okay, to be actually 23 because I kind of consider this as a 23 because this intersect with this vertical lift performance curve, and I estimated this as the 23 million standard cubic feet per day or production per well. Okay, this is important. This is the production of one well profile. Okay, this is not the production of multiple wells profile. Okay, and then what does the question ask me? It asks me, gas sale contract calls for peak delivery of 130 million standard cubic feet per day per year. Okay, this is important. Okay, so in oil and gas industry, it is very important to know the numbers and what this actually represent. Okay, so 130 million standard cubic feet per day per year. So that means this is per day, and we have to times with 365 to actually know how much amount we need to produce according to the contract. And it has an average sale of 95% maximum. Okay, so we got the 130 SCF per day profile times 365. We got this as the yearly production, and it says 95% is sold. So we got to time with 0.95, and it will give us the amount. Okay, so I hope you understand that. So what does it actually want me to do? It asks me to calculate the number of wells initially needed, or the number of wells that we need to actually implement to make sure that we are delivering the promised amount. Okay, so the required delivery per day, just per day, before we talk about per year, is 130 million standard cubic feet per day, as given in the question over here. So we need to actually calculate how much amount of well per day is needed to actually deliver this amount, right? So what do we need to do is we got the maximum production rate, which is 23. And if we divide this 130 by 23, it will give us the amount of wells that we need. Okay, I will show you. So, let me go back to the pen. So this 130 divided by 23. Why do we do that? Okay, we do that because this is required amount of production per day needed to meet the contract. Okay, let's say to meet the contract. And this 23 SCFD is the maximum production that we're gonna produce from the well. And if you actually divide this value, the unit will disappear, and you will actually get this number, which is 5.65 amount of wells needed. Okay, in practice we can't actually do 5.65, right? So we got to actually drill 6 wells to meet the production profile. So we would just write it down over here as 6. Okay, so we got the answer to their question, which is number of wells initially needed, initial number of wells, assuming that the wells are producing with the maximum amount of flow rate according to the vertical lift performance, and we get 6 as the initial number of wells needed. And then it asks us to calculate the sale volume per year, annual sales in BCF, which is billion, remember, 10 to the power 9 divided per year. So they want annual sale amount. Okay, so what do we need to do to get the annual sale amount? Okay, so what do we need to do is we actually got the per day amount, right? And then if we actually multiply that by 365, we will get the per year production profile, which is over here. So 130 divided by multiplied it by 365. So we got the yearly production of 47450 million standard cubic feet per year as our yearly production. Yearly production. And what do we need to do is we need to multiply this by 9.5. Do you remember that? 9.5. 0.95, because we got the 95% sale as average. So we actually need to multiply this by, which is the required delivery per year, times this by 95%, and then times this by 0.001. The reason why I'm adding 001 is it want us to actually say it in billion standard cubic feet per year. So we need to multiply this with 0.001, and then it gives us the number of 45.0775 billion standard cubic feet per year is sold. Okay, this amount is, there you go. This is where these oil executive are interested. Okay, how much are we getting sold? Okay, this 45. This is the amount it is getting sold per year. And if you actually multiply this by the cash, such as, let's say, how much is worth for 1 billion standard cubic feet, let's say, maybe $1,000, $2,000, and you just multiply this and you actually get the idea of how much you will be earning. This is what shareholders and stakeholders are interested okay, so this is how you actually calculate how much is being sold to the market after you have produced with 130 million standard cubic feet per day in a year. Okay, so this is the amount. So we got it. So it asks us to calculate the sale volume per year. We have actually calculated to be 45.0775 billion standard cubic feet per year is sold. Okay, it's finished. So to make sure that we know what we have actually calculated, let's just get a tick over everything that we have done through. Okay, we got it. And then another question. So these questions are designed to actually slightly complicate and make the calculation a little bit complicated. So let's say it says the gas sales contract calls for 130 million standard cubic feet per day for 10 years. Okay, so they want us to produce this amount per day in a year for 10 years. Okay, if you don't really clear, let me say it again. They want us to produce 130 million standard cubic feet per day in a year for 10 years. Okay, so they ask, calculate the sale volumes after 10 years. So they want us to calculate the sale volume after 10 years. So let's, before we actually go into the spreadsheet, let's break it down piece by piece so that we actually know what we are doing. So they want us to produce 130 million standard cubic feet per day per year, okay, for 10 years. So 130 million standard cubic feet and times that with 365 give us 1 year annual, 1 year production, which we actually did, if you remember just now. So if you multiply this with 10 for 10 year, you get the 10-year production. Okay, you get the 10-year production profile, and then you try to multiply this with the 95% sale times 95, and it's going to give you 10-year production with the average sale amount, and it will give you amount that you actually sold, amount you sold in 10 years. Okay, and this will help us to actually calculate the cash flow. So this is the breakdown of how we're going to calculate. Okay, so this is saying that average sales of 95% a maximum. So it is constantly assuming that every year the gas are sold for 95%. But in the real world scenario, it might be different. Some year it could be 70, some year it could be like 60. It could actually vary. But because this is 95, we actually assume it for 10 years. We sell 95% every year for 10 years straight. Okay. So you remember this breakdown, right? We just went through for 10-year profile. So let's actually go to the calculation. So we got the sale volume after 10 years as easy. We got annual sale volume per year, which we just calculated by actually multiplying this required delivery per year with 10, and then you actually multiply with the 95% sale, and it will give you the sale volume after 10 years in billion standard cubic feet. Okay, this is the breakdown that I just explained to you, but
most of the steps are already done in the previous question. So what we needed to do was actually multiply this with 10, and it will give us how much amount of billion standard cubic feet of gas is sold in 10 years. Okay. And then what they ask me, what do they ask me? They ask me, oh, this is interesting now. They ask me, estimate the reservoir pressure after 10 years. Okay, this is slightly getting tricky now. They want to know the reservoir pressure, which is after 10 years. Okay, so we actually need to use the graph to actually understand that. But before we actually understand that, there is something that I need to stress before we as a together look through this reservoir pressure and bottom hole flowing pressure. Okay, so let me just write it over here. Okay, so what do we need to know is reservoir pressure is not equal to flowing bottom hole pressure. Okay, considering that the well is flowing. Okay, considering well flows. Okay, why is that? Okay, if you could please just pause the video and think about it. Why do you need to actually, they are not equal, and considering the well flow? Okay, considering that you have actually paused it, let me give you the answer. So as I said, for well to flow, we have to create the pressure relief regime, not area, profile, right? So we actually need to create drawdown. Okay, well only flow when pressure drawdown is created, and pressure drawdown is actually reservoir minus flowing bottom hole pressure. So what are we going to get is we're going to get a drawdown value, and the bigger the drawdown value, the bigger the production rate. Okay, so P reservoir is not equal to the flowing production profile. We get it. Okay, but there is a condition where P reservoir is actually equal to the flowing bottom hole pressure. Okay, when is that? Okay, considering the well flow in the first scenario, just the well doesn't flow. Because when the well doesn't flow, basically you just actually shut in the well and you wait for some time, and the pressure will accumulate and come back to its original reservoir pressure. Sorry, not original reservoir pressure, its estimated reservoir pressure after time of production, and it will give you the flowing bottom hole pressure, which is the same as the reservoir pressure. So what the question was asking us is to actually estimate the reservoir pressure after 10 years. Okay, so do you want to brainstorm a little bit and think about how do we actually do this problem by pausing the video? And considering that you paused the video, we need to first think about what kind of data do we have and what kind of information do we have. All right, so the data we have is this P over Z value divided by, sorry, not divided, against the cumulative gas production profile. We have created ourselves a inflow performance and trend, linear trend, with the vertical lift performance curve given. And just with this two graph, and also having the data, which we just calculated together, we can actually estimate that. Okay, so step number one. Okay, they ask me reservoir pressure after 10 years. So that means you have produced for 10 years. So you need to know what is the cumulative production after 10 years. Okay, so step 2, find cumulative production, and we have already done that, which is the production of gas by meeting 130 million standard cubic feet per day per year for 10 years straight. And there is a trick to that, because you might say, okay, we have already calculated the 10-year stuff as well over here. But you must remember, this was calculated by considering 95% sale volume. That means there is 5% left that we haven't sold. Maybe we re-inject it into the gas reservoir to make sure the production is well. I don't know, but we need to consider
that there is 5% left every year, which was produced from reservoir. So we need to assume that 100% is sold. Only then we will get the cumulative production. 100% is 100% of what we produce is sold to the market. Okay, in that case, we will get the cumulative production. Okay, so after 10 years, by the way. And so how do we calculate that? So we have the required delivery per day of 130 million standard cubic feet. And when we multiply that, we have the, required delivery amount in a year. And then if we try to multiply this with 10 as for 10 years, we get the sale volume after 10 years, considering that 100% is sold. So we got the amount that is produced, which is cumulative production after 10 years. And that thing, okay, so cumulative production after 10 years. So that value over here, this 474, which we calculated considering 100% of what we produce is sold, is the cumulative production. Okay, so then step 3, what do we do? Use the graph, right? We're given the cumulative production profile against reservoir pressure, declining, reservoir pressure trend. And I must stress you again, this is not pressure itself. It is divided by the Z factor. In the real world, if you have the compressibility factor value, we have to actually multiply or divide that to actually get the real reservoir value, pressure value. But here, we're just using as a reservoir pressure because we're not given a Z. So we have the cumulative production, which is 474.5 billion standard cubic feet, which is MMM. And let's see the amount, MMM as well, so we can correctly use the value that we're going to predict. Okay, so 474, where do you reckon that we place our line to actually find where we have produced? So cumulative gas production that we have produced after 10 years is, after 10 years is 474, right? I don't really remember the figure, which is above. We can look at it. But let's just consider 474, and let's find where the 474 is. And I consider this as just before it reaches to, 500. So I place my red line over here, look at the intersection point, and then draw the line all the way over here. If you actually, I got lost. Okay, let's go again. You see the cursor following, and this is the intersection point. Here it is. And it gives us the value of 1000, between 1500. The first line is 1100 psi as the reservoir pressure. Okay, so as I explained, we just got it. Use the graph. Step 4, look for intersection. And there we have it. We got the reservoir pressure after 10 years of production. But remember, in this case, we are purely assuming that we don't have the compressibility factor and we're just reading off the graph. But in the real world, it could differ. You could actually have to, multiply or divide with the compressibility factor to get the correct value. Okay. So there is one thing to actually consider. It asks us how much is a reservoir pressure after 10 years. So as I explained to you, to do that, we must close the well, right? Only then, when the well is not flowing, the following bottom hole pressure will be equal to the reservoir pressure. So this is a trick that you need to remember. So just like that, we have, look for the intersection point, trace it, and we got 1100 psi. I have written here, pressure of reservoir after 10 years, which is 1100 psi. Okay, so we have successfully gone through here, this one and this one. Okay, so what does the question number 4 ask us? Estimate the new maximum well flow rate after 10 years. Okay, draw new reservoir inflow performance. Estimate a new maximum well flow rate after 10 years. Okay, so we got the production which has been going on for 10 years. Okay, the scenario is we sold, this amount
which is 450.775 with average of 95% sale volume per year. And they want us to actually find out after 10 years of production how much the well is actually flowing. Okay, so what do we need to do is we need to really consider what kind of data that we have. As I said, we got a lot of data. We just calculated a lot of values, and there is one significant data that we just found since from the start, which is actually looking at the production range. You see, production range, and this bottom of the vertical flow performance is, vertical lift performance, if you remember, is the pressure where the well will stop flowing, and we have estimated the new reservoir pressure, which is 1,100 after 10 years of production. So we just need to trace that 1,000 and then 100, line to actually look at the flow rate of the well that is going to be flowing. Okay, so we got the 1,000 over here, and maybe slightly above 1,100 right over here. Okay, 1,100 psi of reservoir pressure when the well has closed. And if we trace all the way here, we're going to be getting the rate, which is slightly less than the maximum flow rate, right? So the point of intersection is where we estimate the new flow rate after 10 years of production. So just read off from the data. I consider this as a 21 because it is pretty close to 21, considering this is 25, 30. So we got the new well flow rate after 10 years, which is 21, remember, million standard cubic feet per day. Units are very important per well as well, because this is like one well production profile. So they want us to actually figure out per flow rate after 10 year, which we did by reading of the pressure value, which is the 10 year. Let's say read 10 year after production reservoir pressure, which is 1,100. And just like that, we look at the graph and we look at the intersection point, and we actually estimated how much has been produced. Okay, and another way to actually look at this problem is actually calculate using the material balance approaches, as I have mentioned to you before. This could be another theoretical approach to do that, which we will focus if we have time, and I will do another new video over the well oil field performance, and then I will show you equations of how to do that. Now it asks me to calculate the number of wells now needed. So because we have estimated the flow rate after 10 years, which is less than flow rate at the start of the production, they want us to actually calculate the amount of wells that we need to meet the production contract or the sale volume contract. So it is quite simple, really. So the promised amount is to produce 130 million standard cubic feet per day. And we have the flow rate after 10 years, which is 21 million standard cubic feet per day. And then you divide this 130 by 21, and then we get this new number of well, which is 6.197. Okay? Okay. So let me charge my computer real quick. Right. So just like that, we have figured out how many amount of wells that we need to actually produce the promised amount, when we sign the contract, which is 6.19. We can't do that in real world, which is 7. So we need to drill one more additional well to meet the production, contract. Okay. So another one is asking us, okay, we have done this. So if no more wells are drilled what will be the final production rate. Okay, so it is asking us, considering that no more new wells are drilled, and we keep producing in that, wells that we have just implemented, what will be the final production rate? So we need to use this, flow rate, which is produced after 10 years, and then we're gonna have to calculate it. So final Q if no new wells with a new reservoir pressure is made. So we got a new number of well, which is 6.19. I didn't use number 7 because I wanted to be more accurate, but if we want to be more accurate, we could actually use 7, which is more realistic value over amount of well. So we get this flow rate if we actually produce without any new additional wells. So let me just walk you through how we actually did that, okay? So they asked me about the final production rate. So what I did was I used the flow rate, which we estimated using this graph intersection of the new reservoir pressure, and it gives us the flow rate of 21, and then we have number of wells, which is 7, after we estimated how much new wells that we need to implement, and then we multiply this with 365 for a year, so it gives us the final flow rate of okay, actually I made it wrong. It's not 365 per day, just in a day it will be 147 million standard cubic feet per day. The reason I removed this 365 is I calculated it as the annual production profile, but what they ask is just a daily production profile, so it will be 147 with this new number of wells, and it actually meets how much we are required to deliver, right? 130. So we're in the right track. Okay, and this question might mean the other way as well. It might mean, okay, how much will it be produced with the original number of well with the flow rate after 10 years? Then we just need to multiply this with not 7, number 6 over here, and it will give us the different value. So why don't we go ahead and do that? If we actually don't drill any new well, this is the amount that we're gonna produce, and this is not gonna meet how much they required us to produce. So makes sense, right? So this is how the real world business challenges are encountered, and this is how we actually do that. And okay, so we have done this as well, and it asks us estimate the rate at which the well will stall. Okay, this is quite simple. Let's go ahead and look back over what we have discussed. The well is going to stall at the bottom of this vertical lift performance curve, which is the green one. In our case, this blue one, and we have a zoom in picture of this vertical lift performance curve. And if we try to extrapolate how much amount of pressure is needed to actually make the well to flow at the minimum rate, is possibly around, considering this is 250, 500, 750, let's say 125. Okay, it might vary, but let's just take this number 125. Yep, pressure reservoir stall, or the minimum flow rate over here is 125. So we have estimated that as well. So it said estimate the total production at the stall reservoir pressure. Okay, so it wants us to estimate the total production if we are gonna produce at the stall reservoir pressure. Okay, so what do we need to do? We actually need to look at this stall reservoir pressure, which is as we estimated 125, and then if we try to put a straight line across it and look at where it intersects on the x-axis, which is gas production rate per day, and it will give us how much amount of rate is produced at this stall reservoir pressure, which is the minimum flow rate. And I consider this as the 7.5 because this is 5 and this is kind of like in the middle. So the final Q, if, oh sorry, not this one, the total production rate that we have to actually look at is after 10 years, right? At the stall reservoir pressure, and considering that we produce at this rate for 10 years, this is how we calculate it. So the stall flow rate is where I have just, estimated by looking at this graph and the intersection point at the x-axis, and I consider this as a 7.5. So 7.5 times, so 7.5 million standard cubic feet per day is produced per well at this stall reservoir pressure, and multiply this with 365 give us the annual production, with this stall flow rate at the stall reservoir pressure, and then multiply this with 10, gave us the 10-year production profile of gas with this flow rate at the stall reservoir pressure. So since we are talking about only one well profile in this graph, we have to multiply with the amount of well, which is in this case C19 7, and then multiply this with 0.001 to make it as billion, and it will give us the amount of 191.625 billion standard cubic feet that is produced after 10 years as a cumulative production. So I believe you might be a little bit complicated, but I suggest you to go back a little bit and listen very carefully over each term that I read it, to actually come to the answer. Okay, and then this is how we look at it: stall reservoir pressure, total production, and it want us to estimate the recovery factor, which is very easy. We have the gas initially in place, which is 700 billion standard cubic feet, MMM. And we have actually read it, and then we have to divide the production which we produce at this stall reservoir pressure, which is 191.625, and then we divide that by 700, and then multiply with 100, give us the recovery factor of 27.375% as the recovery factor. Okay, so this is how we calculate these kind of flow rate estimation, production forecasting, gas initially in place using the inflow performance curve, and also vertical lift performance curve. This is how we calculate it. But as I said, how can we improve the production? So what we need to know is this inflow performance curve, this blue line or this black line over here, is like something that we cannot change because we have the constraint of the value, which is permeability, viscosity, formation volume factor. These are the things that we cannot change because these are originally the reservoir properties. But what we can change is vertical lift performance, using the tubing size. So this is what I was trying to say. Okay, so let's say this this point over here is where we get the stall and the minimum production, right? And if we use a smaller tubing vertical lift performance, that means changing this curve into a much smaller one, we get the new production profile, which is the new minimum flow rate at stall point and the new maximum flow rate at stall point. And this line between this green and blue line is where we could actually squeeze out over what's left by changing the smaller tubing size. So the point that I was trying to make is this is maybe look very good, yet you can always squeeze out something, and you can always efficiently recover more than you expected. However, there are a lot of constraints in the subsurface in the real world, right? For example, in our problem, we didn't consider the aquifer strength, and then we didn't consider the geomechanic point of view. Okay, what's going to happen to the field stresses if you actually use a smaller tubing? Is it going to be able to withstand it? Or is it going to do the borehole washout? You know, these kind of things are a lot of things that you need to consider, and also you need to think about what type of well that you are using. Are you using the vertical well? Are you using the deviated well? Are you using the horizontal well? And this is going to play a crucial role in deciding the development plan and the well planning strategy. And even though, you know, there are possible solutions to actually squeeze out over what's left in the reservoir, maybe there are like constraints that we cannot actually you know, cross over, and we must stick to what we have with the original vertical flow performance, you know. Or sometime if the opportunity is very good and it is very you know, reasonable with the constraint that we have, we may be able to introduce a smaller tubing to actually squeeze out the more production that we originally estimated to have produced. Okay, guys, so this is everything that I have to share for today. Just to recap, we actually did the, you know, gas initially in place prediction using the pressure against the cumulative gas production profile. We created the inflow performance curve, a vertical lift performance curve, by using the simple formulation given over here, considering that we don't have the another factors such as permeabilities, viscosity, formation volume factor, wellbore radius, skin, etc. And what we did was we actually estimated how these productions are forecasted, how much amount is sold, how many numbers of wells are needed to actually meet the production contract as promised, etc. Okay, so I hope you learned something. And I myself also have to do some more complicated answers, so that questions, so that we can actually walk through more complicated real world scenario. But I guess today is enough for this section, guys. And if I have time, I would do also the you know, oil production, you know, which is slightly different from the gas, and I'm actually still doing that. So okay, so yeah, that's everything. Hope you enjoyed this video.